Water. Our bodies are mostly filled with it. It's all around us and part of vital cycles on the planet that keep the planet alive. We're taught that water has 3 phases: solid, liquid, and gas, and that cell membranes keep the water in our cells. We learn that warm water freezes faster than cold, that water can rise up into the capillary structures of trees, and that clouds are water droplets hanging in the sky. But if we only understand water in the 3 phases that we learn in school, these facts don't actually make sense. What if there's more to water? What if water has a 4th phase, a more cohesive and organized phase that makes everything we know about water make sense? And what if this new understanding of water helps us activate greater states of health and vitality and helps us discover what we need to know to achieve optimal states of wellness? Today's guest is Dr. Gerald Pollack. Jerry Pollack is a scientist recognized worldwide whose passion lies in plumbing the depths of natural truths. He received the first Emoto Peace Prize and is the recipient of the University of Washington's highest honor, the annual Faculty Lecture Award. He is founding editor-in-chief of the research journal Water and director of the Institute for Venture Science. Dr. Pollack's award-winning books include The 4th Phase of Water and Cells, Gels, and the Engines of Life. Today, we're going to discuss new understandings about water, but also the reason why we know so little about not only water, but about the way cells actually work in the body. Please note that we had technical difficulties with this interview, but we thought that the information was so important that my producer, Mark Packard, and I decided to publish it anyway. Please refer to the transcript if you need more clarity about what is being said.
You're listening to Quantum Revolution with Karen Curry Parker, exploring new frontiers in consciousness, science, and evolution. Join us in intimate conversations with cutting-edge scientists, spiritual leaders, artists, disruptors, and visionaries who are working towards reframing the narrative of our future by healing the rift between spirituality and science, reclaiming creativity, and laying the foundation for a new world. And now, here's your host, Karen Curry Parker.
Hi, everyone, and welcome to Quantum Revolution. I'm Karen Curry Parker, and I'm here today talking to Dr. Gerald Pollack. And we're going to be exploring some ideas that I think are going to really cause you to have to rethink just about everything you learned in biology class in high school and beyond. Dr. Pollack, it's so exciting to have you here today. Welcome.
Oh, thanks, Karen. I'm thrilled to be with you and delighted to share what we've learned with the audience.
Awesome. Okay, so I'm just going to dive right in because I've spent the last week plowing through a book called The 4th Phase of Water. I have to be really honest and say that my mind is blown. And I read snippets to my 12-year-old, and we've been walking through the kitchen in deep reverence for water ever since. I want to just give everybody a background because I think sometimes when we walk away from science in high school, we sort of walk away and think, oh, good, I don't ever have to think about that again. And I want to invite you all to stretch your minds and remember that when we were in school, we learned that water has 3 distinct phases: liquid, solid, and vapor. You're saying, Dr. Pollack, that there is actually a 4th phase of water. Talk to me about what exactly is the 4th phase of water.
It's a phase in which the molecules are ordered. We may think of liquid water, and in liquid water, the molecules, the H2O molecules, are bouncing around at a furious number of times per second. And if you were to look at a picture of it, you'd see all the water molecules oriented, an instantaneous picture. All the water molecules are oriented in their own way. It's random. And they're bouncing around furiously. That's liquid water. But in the 4th phase of water, the molecules aren't doing that. Everything is ordered. It's a liquid crystal. It's not exactly liquid. It's not a solid. It's somewhere in between that where the molecules are ordered. They're actually different from what we think of as ordinary water molecules. They've actually undergone a transformation. They're transformed into sheet-like structures with one sheet piling up building on the previous sheet, typically the way it works, the way it builds is if you start with a container of water and you put some material in the water, let's call it a hydrophilic material that is water loving. It's the kind of material where if you had it laid out on a horizontal, if you dropped a droplet of water on it, the water would spread out. Unlike Teflon, for example, a hydrophobic surface, where the water remains beaded up. So when you have hydrophilic surfaces, not all, most hydrophilic surfaces, what happens is when the liquid water meets the hydrophilic surface, the first molecular layer that interfaces with the surface undergoes a radical transformation. And parts of the water molecules, the OH minus, remember you have H plus, OH minus, that water molecule. Of course, they're connected together in one molecule. But in this case, what happens is the OH minuses separate and they gather together in a sheet-like form to build next to the hydrophilic surface. Once that builds, there's a kind of honeycomb-like structure built of hexagons. And once that builds, then the next layer builds. The first layer acts as a template for the buildup of the second layer, and for the third, and so on. And these layers keep building from the liquid water. And this buildup, which can consist of many of these layers on the order of hundreds of thousands of layers, even close to 1 million layers under the appropriate circumstances. And beyond that, beyond those layers, those usually negatively charged layers, OH minus, negatively charged layers, are the positive, the H pluses. They exist beyond this collection of sheets. So the collection of sheets is the fourth phase of water. We call it easy water because it excludes many substances. And beyond it are the complementary positive charges coming from the water. You've got the negatively charged zone, and then the positive charges beyond it. It's like a charged battery. And if you were to put two electrodes in, one in the negative and one in the positive, which we've done in our laboratory, you can light a light bulb. You can get electrical energy from it. In order to charge this battery and to order all those molecules from chaos to order, you need energy to do that. It's like a cell phone. If you fail to plug it in overnight, you won't have a useful cell phone in the morning. And so the same thing occurs. In order to separate the liquid water molecules into the OH minus and the H plus, you need energy to do that. You're separating charges. The energy comes from light, from infrared light, infrared energy that is responsible for breaking up the water molecules into OH minuses, which form the fourth phase or exclusion zone, and H pluses, which sit beyond the exclusion zone. So this battery contains a lot of energy, but I think I should stop now instead of giving a speech because I know you've got dozens of questions.
Actually, you were leading exactly where I was really wanting to go next. The body has a lot of water in it. There's a lot of energy in the body. So how does this information, or does this information, change the nature of how we understand water in the body? And how does it change what we understand? And what are the implications in terms of health and wellness?
Thank you. That's a great question. You have these batteries. This water, this fourth phase water, builds at interfaces. It builds at generally hydrophilic charged surfaces, and your cells are filled with them. It's not just the membrane. Every protein that sits inside your cell and every nucleic acid and all the major stuff that's stuffed into the cell, most of those surfaces are hydrophilic surfaces, and therefore they're exactly the right kinds of surfaces to form easy water, which means that your cells are actually filled with easy water. My first book on the subject, published, now 20 years ago, it's called Cells, Gels, and the Engines of Life. And it talks about the role of water. At that time, we call it structured water, which is what other people who knew something about ordered phases of water tended to call it. It's not a great name because everything has structure. But anyway, we talked about structured water, demonstrated that the water is absolutely central. This structured water, now easy water, is absolutely central for everything that the cell does. That's not what you read in the textbooks, but that's the conclusion that we were able to come to, and a massive amount of evidence presented in that book. Now we know more about that water, and it's the kind of water that I just mentioned to you, which we call easy water, the fourth phase of water. But water contains energy because if you think about the inside of the cell, and if the inside of the cell is filled with that kind of water, I got to digress for just 1 second, just the point that a lot of people would be skeptical. What do you mean our cells are filled with fourth phase water? We always thought the cells are filled with ordinary liquid water. But just think about this. Suppose you cut yourself. If you cut yourself and all the cells are filled with liquid water, the water would come pouring out as it would from a broken pipe, water containing. But as you know, it doesn't. The blood does come out. Of course, it coagulates, but you don't see water gushing out from a wound. It doesn't do that. And you don't suddenly dehydrate when you cut yourself in the kitchen. So I just wanted to digress to bring up that point. So let's see, where was I?
You were talking about easy water in the cell and the fact that all of the insides of the cells contains this easy water that's structured.
Right. Okay.
Yeah.
Thank you. I think many of your listeners may know that the cells are negatively charged. If you were to stick an electrode inside the cell, one inside, one outside, the inside would record a negative electrical potential, typically 50 to 100 millivolts. And this has been known for 50 or 60 years. And the question is, well, how come? And what you may have learned, depending on the courses that you've taken, is that the reason for this has something to do with the membrane and the gadgetry that is sitting in the membrane, pumps, channels, et cetera, et cetera. This story is a bit complicated, and I don't need to go into it. However, if it's filled with easy water, and easy water is negatively charged, then it's a kind of no-brainer that some or all of this negative charge can come from the water itself that's inside the cell. A piece of evidence for this is that you can take a gel, and the inside of the cell is much like a gel, and you can stick the same electrode in the gel as you stuck in the cell, and the result is the same. However, the gel doesn't have a membrane. So if you argue that the reason for this negative electrical charge inside the cell has something to do with membrane gadgetry, then how come you get the same result with no membrane? This is one argument, and there are others in favor of the idea that the cell is filled with negative charge because the water, the easy water, the fourth phase water that fills the cell, is itself negatively charged. Now, if you think of that in terms of energy, which was your original question, think of a bag filled with negative charges. They'll repel each other. They'll want to get away as far away as possible from one another. That's their lowest potential energy state. But when they're stuck together, when they're squeezed together, that's a high potential energy state. The potential energy that wants to get rid of is sitting there inside the cell and getting used. And the arguments that I've put forth in the book that you mentioned, Cells, Gels, and the Engines of Life, and also in the book, The Fourth Phase of Water, that energy is sitting there waiting to be used. And of course, it is used. It's used to do many of the things that we do, or many of the things that our cells do. For example, in the muscle cell, in the relaxed state, when it's not contracting, all of the water, or I say all, but essentially all of the water is sitting in the easy state. And it's got all this negative charge. And then you trigger the muscle to contract. And what happens is that this energy is used to drive the muscle contraction. And all of this negatively charged water gets transformed into ordinary water. And then when the contraction is over, the transition goes back to the ordered, structured, easy water, which requires energy, by the way, to get it going back. And that's why your muscles, if you've overdone it and played 3 matches of tennis, you might find some cramps in your legs and the muscle remains contracted. It can't relax because in order to relax, it needs energy to build up that easy water once again. The main point is that water is essentially full of energy. And the question is, how much of our energy comes from that negative charge? And how much it comes from ATP? Many of us learn that the energy that our cells have comes from adenosine triphosphate, where one of the 3 phosphate bonds has a high energy bond. And that's where we get our energy. That may or may not be true. The reason I raise a doubt is that the doubt has been expressed by a hero of mine, one of the giants on whose shoulders I built, a guy named Gilbert Ling. He passed just shy of 100 years old.
Wow.
And Gilbert came from China. He was selected among all Chinese aspiring scholars. He was one of three. He was the biologist. In Gilbert's website, gilbertling.org, he brings up something really important that all of us seem to have missed. And that is when the idea of a high energy phosphate bond came into being, that would have been about 70 years ago, roughly. He said it was a really powerful contribution because finally people can understand where our energy comes from. And ATP comes out of metabolism. We eat food, we digest it. Out of that comes this high energy phosphate. However, 1 year later, some well-known scientists wrote a paper saying, not true. These guys screwed up. They made a simple arithmetic error. There is no such thing as a high energy bond. It's never been followed up.
Wow.
70 years ago. One doesn't know. Are they correct in this or are they incorrect in their challenge? And it's really too bad because it's a critically important question that we need to address. And I don't know the right answer. I don't know because this is beyond my sphere of expertise. So I'm circling back now. The question is, well, where do we get our energy? We get some of our energy from the mechanism that I've been talking about, these negative charges that want to get away from each other and therefore have the potential to do work, potential energy to drive the proteins to do whatever they do depending on the particular cell. In the muscle cell, it would be to contract. In the nerve cell, it would be to conduct information. And the secretory cell, it would be to secrete, et cetera, et cetera. But some of the energy that's needed to do all these jobs is coming from all these charges that are sitting inside your cell that want to get away from each other. And some of it, most of it, none of it, I don't know, comes from ATP. We don't know. So that's why this is a critical question that needs to be answered. We don't know where our energy is coming from. Is it mostly or almost entirely from ATP? Is it mostly or almost entirely from the charges? We don't know the answer. But I think the charges probably constitute some fraction of the energy that we have. And it's interesting that the source that built this energy is light. It's not a complete surprise if you think about it, because, well, how do plants operate? Step one in photosynthesis is pretty much what I've described to you. It's the breakup of water, of H2O, into negative and positive components, into OH minus and H plus. Step one.
Mm-hmm.
And so what I've been telling you is we like to think of it as a kind of generic form of the first step of photosynthesis. And that makes sense to me. If plants came before us and certain unicellular organisms that basically live on light, the energy comes from light. And what I've been trying to convey is that, yeah, something similar may apply in animals as well. We may actually use light in a way that's analogous to the way that plants use light, but we never think about that. It could be extremely important.
The thing that's sort of coming to me as I think about this, and I keep going back to how many times we draw out photosynthesis in high school and ATP and all those things. And basically what I'm hearing you say is that this basic building block of our understanding of biology and human physiology is maybe, based on what you're sharing with us, maybe not true. And if it's not true, then what I'm hearing you say is that we're going to have to rethink everything that we think of when we talk about how do we heal the body and how do we keep the body healthy? Because, cellular metabolism maybe isn't anything like what we thought it was before. And as I'm hearing you say this, and I'm thinking the implications in terms of how does that affect our understanding of how the nervous system functions? How does that affect the way the musculoskeletal system functions? You're really taking some core ideas, and I'm not saying turning them on their head. You're just shattering old paradigms around how the body actually works. And I'm curious in your explorations around beyond just, of course, the mind-blowing idea that water actually functions very differently in the body, perhaps, than we realize. How has this information been received by the community of scientists within which you work?
Poorly. There is a small community of people who study fundamentals of water. They mostly do computer simulations because studying water is not so simple. And it's not a large community. The response from that community has been either hands off, in other words, wait and see, or decidedly antagonistic to what we've done. There have been maybe 4 or 5 or so published papers that are suggesting that all that we're saying is wrong. And the other side, if you look at the reviews of that fourth phase book, for example, the reviews are simply amazing. As to the acceptance, more than just acceptance, huge enthusiasm from many intelligent, thoughtful people who looked at the evidence, a lot of which is in that fourth phase book. The book, I think, is pretty accessible.
I agree. It's a fun read.
It's a fun read. Thank you. My son, who's actually a sculptor by training, is the artist. And I'm kind of waiting until he finishes his home remodel. I've got 2 books that are almost ready to follow this. And okay, so the views are split. And I'm reminded of one of the statements of the guy who's considered the father of modern biochemistry, Albert St. Georgi, a Hungarian biochemist, I guess, biophysicist. He won a Nobel Prize for discovering vitamin C. He was a Nobelist among Nobelists, extremely creative guy. And one of the things he said really inspires me or buoys my spirits. He said that, he had many, many creative ideas. And he said, the only time that I knew that one of my ideas was onto something really important is when the response was polarized. When some people said, oh, this is utter and complete nonsense. And other people said, this is the best thing since the invention of the wheel. My spirits are buoyed by that because, on the one hand, there are a group of people who have been in the field of water who object either vehemently or, as I said, wait and see. And there are other people on the other side whose enthusiasm is boundless. So you asked me a simple question, how have they all reacted? If I may, your question was actually a conglomerate of a few questions. What is it that we should be believing or not believing, or how much can we trust what's in the textbooks? It's a question that deserves a few words of response. And for me, a half century of doing science, I've drawn a conclusion that may sound slightly arrogant, but here, if I read about some natural phenomenon and I'm giving an explanation, if the explanation is simple, straightforward, I think maybe it's right. If the explanation is so complicated that I've got to scratch my head and wonder and try really hard to understand what they're talking about, I used to think that was a shortcoming on my part, but it may be that it's simply wrong. For example, it could be in the textbooks for several generations. It doesn't mean it's right. If it's complicated and it doesn't make sense to you or to me, my first reaction is, I'm not so sure that this is correct because Mother Nature does her things simply and elegantly. A lot of scientists and philosophers believe that. And for many years, perhaps you're familiar with the concept of Occam's razor.
Yes.
People are not so much aware. It was Newton who came a few centuries later who said, hey, Occam's idea is a pretty cool idea. It relates to the existence of God. I'm thinking about science. I think the same principle applies. If it's simple, you have two ideas. One is simple, the other is complicated. Almost certainly the simpler one is likely to be right. So when I read a textbook now, I didn't do this years ago, and I look and try to understand. And if it's elegant, straightforward, simple, I'm inclined to think, well, it's probably right. If it's complicated and you have to twist your arm to get around it and scratch your head or whatever hair that's left, it's a good chance that it's not correct. And that's fertile ground for exploration. And let me just give you one quick example of that. An example that we all learn about in middle school, it's the structure of the atom.
Uh-huh.
We all learn it's got a nucleus that's got protons and neutrons, and it's got electrons or electron clouds around it. And the model has evolved now to reflect the contribution of quantum mechanics, which is abstract mathematics. As Richard Feynman, the great physicist, said, anybody who claims to understand quantum mechanics or quantum electrodynamics is either a fool or lying because there's no understanding to be had. It's abstract mathematics. So there's nothing intuitive about it. At any rate, back to the essence of the atom is still a nucleus with electron clouds around it. And if you think about it, whether it makes sense or not, you start with the nucleus, you get the neutrons or molecules, they're neutral, but you've got a lot of positive protons, and these positive protons are squeezed together. really tightly together because the nucleus is a very condensed blob. And when you got positive charges that are all squeezed together, just like the negative charges that I was talking about inside the cell, the positive charges are squeezed together. They want to get away from each other, right? And so the nucleus, as conceived, should explode. But that doesn't make sense because it explodes and you have no nucleus left. And so the physicists have actually recognized this early on, and they invented something called the strong force. The strong force is like a special kind of glue that holds it all together, counter the tendency to blast apart. But there's no evidence for the existence of a strong force. It just has to be there if you accept the model. And I think if you were assigned to come up with a model of the atom, and you came up with that one, starting with the nucleus, you'd fail because it doesn't work. You'd be putting on a Band-Aid to cover up a gaping wound.
I think one of the things that I'm hearing you say, this is something that's come up for us a lot in the conversations that we've had over the last season, especially, is that we are entrained, if you will, or conditioned to accept certain basic fundamental ideas. We'll call them ideas. And we've constructed large models of thinking around these core ideas. And there are certain core ideas that, by virtue of people who, like you, are curious and engage in an exploration with an open mind that's rooted in curiosity, start to ask really important questions like, why does this not make sense? Why is this model actually really not a viable model? And I think in the age of scientific exploration that we're in right now, it seems like there are a lot of people, a lot of scientists who are having to work to maintain curiosity and to continue to see the world through a lens of curiosity and be willing to take the courageous step to say, hey, maybe the emperor isn't wearing any clothes. And that if the emperor, in fact, is naked, maybe we need to explore the fundamental building blocks of what we consider to be the core aspects of information in any scientific field that we're in, and to not keep pulling out solutions from a fixed set of solutions. One of the things we talk about a lot, Dr. Pollack, in this podcast is the fact that, if we strictly look at the world through the lens of materialism, that the models that we're looking at seemingly are showing us that we're coming to the potential end of a major phase on this planet as a result of having misused resources and maybe even misunderstood certain core basic elements of science. I think if you really think about the Darwinian model of evolution, that the whole survival of the fittest idea, it hasn't really served us well. And when we're confronted with information that doesn't fit inside the box of what we've known before, we don't know exactly what to do. What do you do when you look at information? What do you do, first of all, to drop any of your preconditioned bias that maybe comes from what you learned and what you thought you knew? And secondly, what do you do to maintain curiosity so that you have an open enough way of thinking that you're willing to look at the information that you gather through a new lens or through a new perspective?
One element of the answer is a sense of confidence that I've gained over the years. Of course, I started like everybody else who starts in science, some degree of timidity. You don't challenge the great authorities in science. But over the years, I've learned that you do challenge the authorities in science. And with me, I began my career in the field of muscle contraction, the molecular mechanism of muscle contraction. I was a graduate student, and I ran into another graduate student who is much more astute than I was. We became friends. Unfortunately, he passed recently. A Japanese guy whose name is Wazumi. And he taught me something right then and there as a graduate student. He says, just because a guy who won a Nobel Prize comes up with a theory doesn't mean the theory is right. And he told me, well, the guy may eat the same food that you eat. He makes love in the same way that you might make love. Just another guy who happens to have won a Nobel Prize. And so that got me thinking. And he was able to convince me within a span of 5 minutes that the theory of muscle contraction that persisted and came forth by a famous Nobel laureate, Sir Andrew Huxley, was wrong. It couldn't be right because he said, look, here's what is being proposed. And he said the whole structure will fly apart during the first contraction because it's unstable. And I have yet to hear one counter. I started in that field half century ago. He's right. It's simply, there's nothing to counter that. And so that kind of began in me to think, well, gee, if that's wrong, what might be right? And I worked for a couple of decades and I wrote a book about muscle contraction. And I think that, that the ideas that are presented there are okay and they fit very nicely. And we were able to obtain some pieces of evidence, or quite a few pieces of evidence that were grossly out of accord with the model put forth by that great Nobel laureate. And that actually formed the foundation for the new theory that I put out. So I'm telling you all of this because what it did was to instill a sense of confidence that, hey, just because there's a theory that's out there, it doesn't mean the theory is correct. And I think that confidence came increasingly as the years went by, because I began listening to what Gilbert Ling and Albert Szent-Györgyi and others had been talking about water, that water in biology is not like water in the glass. And their ideas began to make sense to me, and I began pursuing it. And the feeling of confidence actually increased as these various books were published. The feedback that I got from so many thoughtful people who said, hey, you're right on. And when you get feedback like that, you begin to build a sense of confidence. And when the critiques that appear, and inevitably there will be critiques, because scientists like to hang on to their cherished ideas. They don't like to be challenged in a way. And I saw the critiques, and to me, the critiques were essentially, few of them were really meaningful in any way. And so confidence built. Once you get the confidence to face science and say, as you said, the emperor's new clothes. If the emperor's new clothes are no clothes, it's okay to stand up and say, the emperor's got no clothes. The ultimate is, the reason that propels me, I feel I have a hunger for truth. I really want to know how it works. I have great curiosity. And I think I've developed enough confidence over the years to think that if the ideas that I'm coming up with are not necessarily correct, but at least they're one attempt to bring truth to science. It's obvious that so many people said it, that a beautiful theory can be undermined by only one ugly fact. I don't have that kind of self-confidence to think that every utterance that comes from me is truth. No, by any means. But I feel compelled at least to try. Where a theory doesn't work, it's my duty, it's my objective to tell it like it is. It doesn't work because here are the reasons why it doesn't fit. A, B, C, D. And let's see what might fit.
I love this answer. So confidence, curiosity, and the willingness to explore the potential of there being an ugly fact. Dr. Pollack, I appreciate you joining us today. You've given me a lot to think about. I appreciate your willingness to have the courage to explore some of these topics, because I think there's a rarity among scientists who are willing to explore that ugly fact and be willing to stand with courage and confidence in front of a community that sometimes struggles to rethink paradigms. So I appreciate your willingness to explore so deeply. Your book, The Fourth Phase of Water, is available on Amazon and other online bookstores, and I think probably in bookstores too as well. I really want to also encourage people to go visit your website. Do take a moment to watch the video on Dr. Pollack's homepage. It's a pretty beautiful exploration of why rethinking the way we understand water and how water functions is so important, not just for the sake of understanding the way that we operate on a cellular level, but just because I think it gives us a certain awe of the expansiveness of all of nature's creations.
Well, thank you, Karen. I appreciate your thoughtful and astute questions. They were really inspirational for me.
I, again, appreciate you taking your time to be with us here today, and thank you for joining us.
All of our scientific assumptions about energy and how cells work are wrong because of a math error. What we know as truth in science is perpetuated by myths and assumptions that sound good, but don't always pencil out on paper. what we are taught about science in school is often based on tradition, not, science. We've heard again and again and again in our quantum revolution conversations that we've been privileged to share that science, real science, is in a state of crisis. Data and even research studies are tainted by the hunt for finance and research dollars. Curiosity and the willingness to ask what some scientists think are obvious but challenging questions is regulated and even suppressed by the business of science. In addition to doing groundbreaking research on water and cellular metabolism, Dr. Pollack is also the founder of the Institute for Venture Science. The IVS funds scientific inquiries into high-risk, high-reward theses that challenge conventional thinking. By virtue of their break with ideas that may have become more tradition than forward-looking concepts, these fresh challenges may lead to fundamental breakthroughs in understanding. Scientists, real scientists who are curious and willing to challenge tradition, are being forced to create their own research funding in order to break free from the limitations of having to chase conventional research dollars. In other words, breakthrough discoveries that might hold the elegant solutions to the challenges facing the world today, are often being done in labs who not only have to do the research, but have to fight to find independent funding to do real science. Without independent, non-biased funding for actual research, everything we know as truth might actually just be traditional understandings that are actually, scientifically invalid. I want to honor and acknowledge brave and true scientists such as Gerald Pollack and some of our previous guests, such as Avi Loeb and Amit Goswami, who have had the courage to stake a claim for true curiosity and the willingness to question everything, as good scientists should. It is this quest to understand and explore that promises to help us find the solutions to the challenges facing humanity today. I'm Karen Curry Parker. Thank you for joining me for Quantum Revolution. If you'd like to learn more about your unique way of learning and discovering what is true and right for you, please visit my website, www.quantumalignmentsystem.com.
Thank you for joining us on Quantum Revolution with Karen Curry Parker. For more information on how to change your world and to hear more about our guest today, visit quantumrevolutionpodcast.com. Make sure you follow us on your favorite podcasting platform so you don't miss a single episode of Quantum Revolution. We'll see you next time for some more groundbreaking conversations with Karen and her guests. How will you impact your world today?